Hello, welcome back. Today, we want to talk about simplifying radicals with negative numbers. So our goals is to be able to convert, I should say, a radical expression in kind of root with a negative number to I form, and also be able to simplify radicals involving imaginary numbers. So let's take a look. So what we're looking at is something like this. You see right here, expression like this, so the square root of negative 40. I should do this one in a moment. So what we're going to do then is make sure I understand how to simplify it. So the first thing we want to do is convert to I form. That means using one of these rules. And if you've seen a previous video on basics of complex numbers, hope you remember this property. You have the square root of any negative number x on a radical sign that becomes I times the square root of x. So if that's the very first thing we want to put it in that form, and that's when we have it in that form, we simply use the rules of simplifying radicals then to help us out with that. So working with the radical expressions containing negative numbers, convert radicals to I form first and simplify the radicals. Then also, we use this rule. This rule is a rule hopefully you've seen before involving simplifying radicals. And basically, we're going to use it kind of, in this case, from left to right. So where n can be essentially any number, but we're going to focus on, this case, square roots, usually even numbers. As long as the numbers inside are multiplied together, then we can separate them like this. So the square root of x, or the nth root of x times the nth root of y. In doing so, hopefully we can find a perfect square. For example, if it's a square root, we can simplify then what's left over, then put it, that allows us to put the most simplified form. So let's take a look at a couple examples, or a few examples over here. So our directions would just be to simplify. Of course, that means put it in I form, then also make sure your radical is in simplest form possible. Let's take a look at our first one, the square root of negative 49. Okay, so the square root of negative 49. Whereas first, we realize, so this is a negative, just as it here, put in I form. Use this rule right here, right like this. So this becomes then I times the square root of 49. Okay, this property says the square root of negative x is equal to I times the square root of x. So the square root of negative 49 is equal to I times 49. Make that equal sign look a bit better. And we know the square root of 49 is 7. So this you can write either I times 7, or often more typically is 7 times I. Either way is correct. Okay, so now let's do the one we mentioned to begin with, square root of negative 40. All right. So once again, put this in I form first. Let me say first on both of these. That's your first step. So once again, using the property like we did here, this can be I times the square root of 40. Okay. And now we want to simplify, because square root of 40 is one actually we can simplify. So use this property here. What we're looking for are any perfect squares that are in 40. 40 itself is not a perfect square like 49 was. Are there any perfect squares in 40? Yeah, there is. So one way we can write this is I, and then 40 is the same as 4 times 10. Okay. Now what we want to do then is use, use this property of radicals. It says right here, now I can, since I'm multiplying on the inside, I can break this up into I times the square root of 4 times the square root of 10. Okay, so now, the square root of 4 is 2. This can be I times 2 times the square root of 10. Now, are there any perfect squares in 10? None other than 1, and 1 we don't count. So actually this, once again, it's usually probably written more commonly like this: 2 times the square root of 10 times I is our final answer. Okay, either way is perfectly fine. It's more commonly written this way. Just make sure it's clear that your I is not under your radical here. Okay, remember we stopped because there are no perfect squares in 10 besides 1, and we don't count 1. Okay, let's take a look at our next example. let's just start here on page number 2. So number 3, this time let's say we're actually adding a couple of radicals. So negative 48, square root of negative 48, plus the square root of 12. Rather the square root of negative 12. Okay. Now, first off, our general rule about adding and subtracting radicals, they have to be like terms, or adding, subtracting anything have to be like terms. In terms of radicals, like terms means you have the same radical, like you have the same root, like square root, cube root, whatever, and then you have the same thing under the root. So clearly we can't combine these yet. So once again, like we did before, we'll put in I form first. And so we have I times the square root of 48. And then we have plus then I times the square root of 12. Then we want to simplify the radicals if we can. Because these are still not like terms, so we can add them as they are. Once again, we're going to use this property. Now here, 48 is one that can be a little, sometimes you may have to take more than one step. There are actually a couple of perfect squares in 48. 48 itself is not one. Now you can do 4 times 12. And that's perfectly fine. But then you have to simplify the square root of 12. So the best thing is you want to pick out the biggest perfect square in a number. In this case, that's 16. So 48 is 16 times 3. And over here, we can simplify the square root of 12. 12 itself is not a perfect square. We can write 12 as 4 times 3. So if we simplify both of these, we have I times, we can break them up. The square root of 16 times the square root of 3. Same over here, use this rule to separate them. The square root of 4 times the square root of 3. So that's going to give us I times 4 times the square root of 3, because the square root of 16 is 4, plus I times 2. Once again, that's 2. Square root of 4 is 2 times the square root of 3. Now, a couple more things. We can't simplify the square root of 3 any further. There's no perfect squares in 3. Now, but these are now like terms, okay? Because we have, in this case, we have i's as well. So to be like terms, have to have I to the same power, which we do. And also we'd have to have the same root and the same thing under the root, which is both square root of 3's. And also, so what we do is combine the coefficients. So let me do one more thing. Let me write both of these as 4 times the square root of 3i, then plus 2 times the square root of 3i. It's not entirely necessary, but it's usually written that way more often. And now, just combine the coefficients in front. Essentially, we have, in each case, we have a square root of 3 times I. So here we have 4 of them. Here we have 2 of them. So together, we have 6 square root of 3i. And that now is simplified. It's just in terms of imaginary numbers and in terms of radicals, that's as simplified as we can get. And also, one thing in mind, this one, and think the ones we've done so far, these are all actually they're all complex numbers, because every number is a complex number. But these are strictly imaginary numbers because they all have an I multiplied by them. Okay, number 4. Number 4, in this case, we are multiplying radicals together. So negative 20 square root of negative 27 times the square root of negative 20. Okay, now, once again, I'm not going to write it. Once again, as usual, first put in I form. So it's going to be I times the square root of 27 times I times the square root of 20. Okay, now, since we're multiplying, we can multiply in any order. And so I'm going to put my i's together and make this I squared times the square root of 27 times the square root of 20. Now, in the same way, we also want to simplify these radicals if we can. So take a look at each one. And also remember that I squared is equal to negative 1. This is going to become a negative 1 out front, which is be a negative sign. Now, 27 has a perfect square root, which is 9. So 27 is 9 times 3. And 20 is 4 times 5. Okay. So again, use this rule, break everything up. I'm going to put this now as just a negative out front. The square root of 9 times the square root of 3 times the square root of 4 times the square root of 5. Okay. And of course, we know that 9, square root of 9 is 3. and the square root of 3. Then we still have times square root of 4 is 2 times the square root of 5. Now, here we can multiply, remember, we can multiply in any order, as long as you do everything correctly. But this is still negative. Now, we can make this as 3 times 2, which is 6, and then we still have the square root of 3 times the square root of 5. And now we can actually use this property here backwards. Okay, we can also combine these. All right, now also I should mention that, of course, the square root of 3 and square root of 5 can't be simplified further separately. So now we can combine these radicals because they're both square roots and we're multiplying them together. So now this can be negative 6 times the square root of 3 times 5 on the inside, which of course, after all this, is negative 6 times the square root of 15. Okay. Now, once again, check, there are no perfect squares in 15, so that's our final answer. Notice this time, this is strictly a real number. Okay, there's no I there, so it's just a real number. All right, let's take a look at a couple more examples. Practice with this. So, number 5, we have square root of 3 in parentheses, square root of negative 3 in parentheses, then the whole thing is squared. Okay, and once again, we're going to do this the same way because this also follows order of operations. You do this in parentheses first. And so let's go write a radical, put it in I form as I times the square root of 3 squared. Okay, now, one thing hopefully you've seen before, you remember from working with powers, is that if you're multiplying something, multiplying two different things on the inside, you're just multiplying the power of the outside, you raise each one to that power. So this is going to be I squared, then times the square root of 3 squared. At this point, also, if you could simplify this to the root, you could. In this case, we can't. Square root of 3 can't be simplified. So once again, since we're multiplying in between, we raise each one to that power. If we're adding, this is like I plus the square root of 3. We couldn't do this. Now, once again, we just saw the I squared is negative 1. And if you square a square root, you get what's underneath, which is 3. And so this just becomes negative 3. Okay, let's look at our last example. This is going to be a bit different, and this is kind of result you often get when solving a quadratic equation using the quadratic formula. Negative 6 plus the square root of negative 81 over 2. Once again, as I said, this is the sort of thing you often get when you're solving a quadratic equation using the quadratic formula. So once again, simplify put it in I form first. So I have negative 6 plus I times the square root of 81 over 2. And then, of course, the square root of 81 is 9. So I have negative 6 plus, I'm going to write this as 9i, though it doesn't matter. I can go first, but usually it's written last, over 2. And then finally, we want to write, it's typically with complex numbers, this is a complex number. We'll have a real part and imaginary part. You want to write this in a plus bi form. So since we're adding here, we can separate this into two fractions. Negative 6 over 2 plus 9i over 2. And we can actually simplify the first one. Negative 6 over 2 is negative 3. Then plus, we can't simplify 9 over 2, so just leave that as 9 squared times I, and that's our simplified result. And once again, this is often, as I said, the kind of solution you'll get with when solving a quadratic equation with a quadratic formula. So what we've learned today is how to simplify radicals involving negative numbers on the inside. So once again, the rule, put it in I form first, like we did here, then simplify the radical as best you can using this rule. Thank you. Have a good day.